Good evening. My name is Mark Checkle-Bain, and I'm the Community Relations Officer for the Berkeley Lab. And how many of you are here at the Friends of Science of the Theater for the first time? Wow, a lot. Well, welcome. We're really, really glad to have you here tonight. I thank you on behalf of the lab for your interest in scientific research being done at the Berkeley Lab. And we'd like to thank our many co-sponsors, including, let me see if I can go back a slide. UC Berkeley, the Chabot Space and Science Center, the Exploratorium, the Osher Lifelong Learning Institute at Berkeley, the Lawrence Hall of Science, and the science departments of the Albany, Berkeley, and Oakland high schools. Logistically tonight, if you haven't been here before, our speaker will talk for about an hour. Then the audience will have plenty of time for questions. We ask that you just raise your hands, and he'll call on you, and he'll just repeat the question. And so just try and project your voice to make sure that he can hear you. The acoustics are actually pretty good in here. So before we start, just a few updates of things that I wanted to tell those of you that were here 3 weeks ago, just a few things that have happened in just the last 3 weeks at the lab. First of all, we announced a new India Energy R&D program at the lab, along with UC Berkeley. It's a joint research development program in which researchers will be working with the government and private sectors of India to develop paths toward reducing the emissions of greenhouse gases while maintaining sustained economic growth. If you remember from our last talk, we talked about India and China, and as they develop more and more, the impact on global warming. And we're not only doing that work in India, but also in China. In addition, the Wall Street Journal gave us an award for the Philo chip technology, a bronze medal, and that was for a DNA chip that was developed at the lab that speeds the identification of harmful bacteria, and that was just announced at the end of September. And one more thing we wanted to talk to you about. How many of you saw some of our researchers at the lab after the last debate last week on Channel 7? Anybody? So we had 3 of our researchers after the debate last Tuesday night. Paul Avasados, Jay Kiesling, and Blake Simmons were interviewed on the program about energy innovation. And it included footage from our new J-Bay facility for next-generation biofuels research that's down in Emeryville. So those are just 3 of the many exciting things that have been happening at the lab over the past few weeks. But tonight, we're very honored to have our presenter here, someone whose class was voted as the best class at UC Berkeley, Richard Muller. Richard Muller is a senior scientist with the lab and a professor of physics at Cal, from where he also earned his PhD under Nobel laureate Luis Alvarez. After earning his PhD, Dr. Muller instigated a series of innovative physics projects, including a study of cosmic microwave radiation, which eventually led to a Nobel Prize for his protege, George Smoot. Dr. Muller developed a new way to measure radioisotopes and a project to discover supernova exploding stars for use in cosmology, and coined the name Nemesis for a star that he and his colleagues suggested is orbiting the sun at a great distance. He's published over 130 papers, which is quite incredible for those of you that have published papers in your life, in particle physics, cosmology, geosciences, and climate. His achievements have been honored by many awards, including the MacArthur Foundation Genius Award, and he was named by Newsweek as one of the top 25 innovators in the U.S. in all fields. His skill at explaining science to non-scientists was honed over decades of advising top business and government leaders, hence his most recent book, Physics for Future Presidents, which you actually can purchase in the lobby afterwards and get signed. And his talk tonight will be based on his renowned course for non-science students, the best class at Berkeley. So after tonight's talk, we invite you to come and join the conversation out in the hallway. And welcome, Dr. Muller.
Well, thank you very much. Thank you for coming. I do teach this class, Physics for Future Presidents. It used to be called Physics for Dummies. It used to be called Physics for Jocks, Physics for Poets. When I took over the course, I know I love poetry, but I felt there was something more important to do. We don't have enough science at our high levels of leadership. And as a result, we make some mistakes. I can give examples. The hydrogen economy, which was touted in the 2003 State of the Union speech, and not really mentioned since then. I think the president learned some physics in the interim. I walk into my class, and I have 500 students in my class, and I built it up to 500. I wanted everybody at Berkeley to take my course. I want everybody everywhere to take my course, because I walk into that class, and every time I'm about to go in, I think to myself, 20 years from now, one of these kids might be the President of the United States. What is it that I will kick myself for not having taught? So it turns out if the rule of thumb is, if it's not important, obviously important, I leave it out. You can easily fill up a semester with things in physics that are obviously important. And I try to distill those into my book for people who don't have enough time to take the course. By the way, the course is all online. And if you want to watch my lectures online, they're all available. Just Google me and you'll find that. There are a lot of them on YouTube, but more of the lectures are on my class website. What I'm going to do today is, the book distills the course. It covers 5 major topics. What I'm going to do now is cover all 5 of those topics in under an hour. So we're going to go kind of fast. You may not learn everything in my lecture. Don't worry about that. What I want you to come away with is the sense that, yes, this is stuff that you need to know. I hope there will be nothing in my lecture that you'll say, why would I have to know that? And also, it's material that obviously you can know. I tell my students that many of them, half of them, I exchange email with my students, and half of them either hate physics or are afraid of it. And usually that's because they ran into some bad teacher somewhere along the way. So anyway, the course, they don't have time to learn the math, my students, or possibly the inclination, because there are other things they consider more important. So typically what I do is I say, here's elementary physics, then here's all the math, and here's the advanced physics. So since you don't have the time to learn the math, we're just going to skip up to the advanced physics. And that's what we'll do now. So this is drawn by a friend of mine. Don't know if you recognize those. Here are the 5 topics we're going to cover very quickly. Terrorism, energy, nukes, space, and climate change. Okay, what do we worry about terrorism? Well, nukes, right? This is in the news. People worry about this. Let me very quickly go through the basic element. We spend a week on this in my class. But let me very quickly go through the basics of nuclear weapons as they might be used by terrorists or rogue nations. So there are 2 fundamental kinds of nuclear bombs. There are 3 if you include thermonuclear, but we don't worry about rogue nations getting them. They're too difficult to do. A major country like China or Russia, of course, they could do that. You put in hundreds of billions of dollars, you can develop thermonuclear. But let's just look at the elementary ones, the ones that we worry about terrorists and rogue nations. The first one is the uranium bomb. Uses an isotope of uranium called uranium-235. That's less than 1% of ordinary uranium. Ordinary uranium, you can't make a bomb out of it. You can make a nuclear reactor, but you can't make a bomb. It has to be purified to make it out of uranium. Typically, nearly 100%. That's exceedingly hard to do. That's the main barrier to making a bomb out of uranium, is the purification of the uranium. You can't purify it chemically because it's just uranium. So once you've purified it, then the bomb is relatively easy to make. And this is what gives rise to the stories that a high school student could make an atomic bomb. Answer is, yeah, I probably could if he got the purified uranium. So there's a lot of interest in purified uranium, people pretending to sell it, people actually selling it. The markets for purified uranium is something we really worry about. So our first uranium bomb was used to kill the people of Hiroshima and to destroy that city. That bomb was never tested. The test in Alamogordo was actually a different kind of design. That was the plutonium bomb. The bomb that we dropped in Hiroshima had never been tested because it had essentially all of our uranium in it, all of our purified uranium. We tested it, we would not have a bomb left. So it was not tested, but because they had purified the uranium, they knew the design was easy, they knew it would work. Destroyed Hiroshima. Now, I'll mention that this is the bomb that Saddam Hussein was building. Wait, you say, but he wasn't building a bomb. You're confusing the second Gulf War with the first Gulf War. I'll remind you about the difference in just a moment. Plutonium bombs. It's relatively easy to get plutonium. All you need is a nuclear reactor. Plutonium is produced in a nuclear reactor. And then you get the fuel, and you separate out the plutonium, which is relatively easy to do if you don't mind handling radioactive materials. It's just much, much easier than purifying uranium. So the plutonium, these two kinds of bombs, if you're president, you need to know the difference. The plutonium you get from a nuclear reactor, when North Korea tells us no more inspections on their nuclear reactors, that's because they want to remove the plutonium and make a plutonium bomb out of it, which they did. Plutonium bomb was used to destroy Nagasaki. We built one. They're very hard to make work. You can get the plutonium relatively easily, but then what you have to do, plutonium can't be used in a simple gun where you bring together two half critical masses and make one critical mass. Instead, you have to put it into a spherical shell and then squeeze it like a water balloon to increase the density by a huge factor. That's very hard to do. Most of the time you do that, the water squirts out between your fingers, I mean the plutonium. Okay, so it's very hard to do. We did it. We had a test because we weren't sure it would work. The test was Alamogordo. It worked, the Trinity test site. And then we dropped the second one in over Nagasaki, killing 150,000 people. The numbers are horrendous, doesn't matter which it is. And this is also the bomb that North Korea exploded in their test 2 years ago. So let's get back to Saddam. Prior to the first Gulf War, he had an active program to make nuclear weapons. This is not disputed. It's just forgotten. This is a photograph taken by the United Nations of the device that he had used to purify uranium. He wasn't up to 100%. He was only about 35%. He starts with something that's less than 1%, gets up to 35%. That's more than halfway there. And then the Gulf War came in. The UN inspectors went in. They found his program, and they destroyed the devices that were being used. Now, this came as a shock to me because I have worked in intelligence analysis, and I know the people who were doing this. And people have been looking for, how do you purify uranium? Well, probably with centrifuges. You hear about centrifuges in the news. Centrifuges, you spin the uranium really, really fast. The heavy uranium goes to the outside. You pull off the lighter stuff. This is the modern way of doing it. This is indeed what is happening in Iran these days. They have a centrifuge plant, which they are using to purify uranium. But there's no evidence that Saddam had centrifuges. You could use laser enrichment. We've actually done that. That's really hard. No evidence he was trying to do that. You could use diffusion plants. Diffusion plants are what we use in the US now. Those are big and very expensive. No evidence of that. So there didn't seem to be any evidence that he was doing it. And then the UN went in and they found this device here, it turns out is a copy of the device that was used by Lawrence to purify the uranium for the Hiroshima bomb. It was the old technology of World War II. Saddam had been using maybe the EWOC technology. He had gone back to the real simple basics to make his bomb. This thing was invented by Lawrence, of Lawrence Berkeley Laboratory fame. It was used to produce essentially all the uranium for the Hiroshima bomb. This was a copy of it. This thing, when you stand it up, it's shaped like a big letter C. And Lawrence named it the Calutron, named after Cal. And that was used to destroy Hiroshima. It's a little bit of a legacy that you don't hear too much about when you're visiting Cal. Anyway, so that's now let's take the North Korean nuke. They actually separated their uranium, they imploded it, they released an explosion, a nuclear explosion. Imagine if that explosion had actually hit San Francisco. How much damage would have been done? Here's the answer. The blue circle and the red circle in the middle are basically the buildings that would be destroyed. Debris would fly out to the yellow circle. Most people look at that and say, that's kind of small. And it is. The North Korean nuke was kind of small. It was best estimate that it was about 40 times smaller than our first plutonium bomb. It was about 400 tons of TNT equivalent. It was a fizzle. Why did it fizzle? There are several possible reasons. Maybe the implosion didn't go quite right. Maybe they had left it in the reactor too long, and there was some of the pollutant, plutonium-240, in there. My students learn all about these details. They're really not that hard to understand. And anyway, it was a fizzle. How much damage is that? Well, if you look at that, that's sort of like a World Trade Center, right? Actually, no. A World Trade Center was worse. Sorry to show this again. I know it's terrible to watch it. Let me talk about I'll talk about the collapse of the World Trade Center in just a moment. But in the World Trade Center, a 767 airplane went into that building. It carried with it 60 tons of jet fuel. I'll show you in a moment that 60 tons of jet fuel contain the energy equivalent of 900 tons of TNT. That's more than twice the energy of the North Korean nuke. One of the things I advise the government on is I think that conventional attacks from terrorists are a bigger threat than a nuclear attack. Nukes are really hard to get to work. Even North Korea, who starved its people to be able to make a bomb, and that bomb was a fizzle releasing less energy than the airplane going in. Let me just talk quickly about what happened to the World Trade Center, because most people don't seem to understand this. This kind of collapse of a building had never taken place before, was unanticipated. If it had been anticipated, the police and the firemen would not have set up in the base of the building. What happened is there was extensive burning where the airplane hit at that level. Now, what does burning do to the columns that are supporting the building? They were designed to stand an hour or two against ordinary burning, but this was 60 tons of jet fuel, equivalent to 900 tons of TNT. Jet fuel has more energy in it, 15 times more energy in it than does TNT. I'll show you that. We'll come back to that in a moment. So these columns, what happens when they get hot? The molecules in them bounce around. That's what heat is. It's molecules bouncing around. As they bounce around, on average, they get a little bit further apart. That's why when you heat things up, they get larger. That's why we have cracks in our sidewalks, because the concrete expands when it gets hot because the molecules are moving faster. But when the molecules are a little bit further apart, the binding isn't quite as strong. And that means they're a little bit weaker. Now, these columns are designed to hold up the building with a considerable safety factor, probably my wife would know, but she is a structural engineer. Let's say 50%. But they weaken. And when they weaken from the heat, which was unprecedented because nobody expected 60 tons of jet fuel to be burning up in the building, when they weaken, now you have a column that's weak. And to know what interesting thing happens, take a soda straw. See if you can find a paper soda straw. And put it between your hands. And push. And it's amazingly strong. I mean, consider it's paper. And then suddenly, you're pushing harder, harder, harder. Suddenly it collapses catastrophically because it bends a little bit. When it bends, it loses all of its strength. Then it's just paper. It doesn't have the strength, the barrel strength. So true of columns, once they begin to go, they go catastrophically. At this point, the upper part of the building comes crashing down on the bottom part, on the next floor. This doesn't have to be weakened because now we have the hammer effect. Put a hammer on your hand and feel the force. Now swing the hammer and feel the force. There's a force multiplier. The force multiplier is just the ratio of the distances. The distance over which you swing divided by the distance in which you stop it. And that gives you the force multiplier. You can take a hammer that weighs a pound and get 500 pounds of force on it, on a nail. So the same thing here, the hammer effect. As this thing comes crashing down, now you're multiplying the force in the lower columns, and they just go too. And so this thing goes into virtual free fall. I watched that happen on 9/11, and I understood immediately what had happened. On 9/12, I went to my class and explained what happened. This thing went all the way down. The remaining jet fuel spread out. Eventually, a similar thing happened to Building 7. But it's absolutely straightforward, but unanticipated by anybody, including Osama bin Laden. We can come back to that in questions if you want. Let me go on now to the next subject. Let me go on to radioactivity. Interesting subject. I have a slide here that I'll show in a moment. I'll begin this by giving one of my favorite examples. I give this just to sort of shock you. I mean, the first thing is, I'll tell you, your seats in this auditorium are radioactive. The book I'm selling is radioactive. In fact, US government regulation is that you may not legally sell alcohol for consumption unless it is radioactive. It has to have a minimum of 400 nuclear decays per minute in every liter of alcohol. That seems paradoxical. Why is this? Well, the US government has decided over the years that alcohol to be legally drunk must come from grain or from grapes or from fruit, from some living material. It turns out all living material is radioactive. That's because the carbon dioxide in the air contains radiocarbon, a radioactive form of carbon. That comes from the cosmic rays hitting the atmosphere. So the atmosphere is radioactive. I love to show this to my class. I turn on a guided counter, click, 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 click. Where's that coming from? The air is radioactive. Plants take in the carbon dioxide, in along with it, they take the radiocarbon. We eat the plants. Carbohydrates are full of radioactive carbon. And so we consume this alcohol, gets it, if it's made from plants. If it is made from fossil fuel, well, that fossil fuel has been down under the ground for so long that the radiocarbon has all decayed away. And so you can tell whether it was made from fossil fuel by the simple measure of its radioactivity. If it's not radioactive, it was made from fossil fuel, US regulations, illegal, they actually do the test. So we are all radioactive. This puts radioactivity in perspective. Yes, we're radioactive. There is a natural level of radioactivity. At 3 Mile Island, after the reactor leaked some radioactivity, people got out Geiger counters and they discovered radioactivity. They didn't realize that there is a natural radioactivity. In fact, they were all seeing natural levels of radioactivity. But they didn't know that. Is it possible to make a radiological bomb, a dirty bomb? Yes, it is. And this is from a famous Scientific American article that talks, I mean, you talk about worst case scenarios. Here it is, and spreading out over Manhattan with large levels. It turns out to be extremely difficult to do this. And I've written some op-ed pieces and some other things. I've written things for Technology Review. The experts know how difficult it is to do this. The reason is simple. Radioactivity has basically two effects. One, it can kill you by radiation illness. You know what this is if you or a friend or a relative has undergone radiation therapy. They get ill, nauseated. And if they get too intense a dose of radioactivity, you die. That's called radiation illness. Litvinenko, the former KGB man who was assassinated by having radioactivity injected into his veins, I guess he swallowed it. That was polonium-210 that he used. When that happened, everybody was saying that it obviously had to be Putin because just to get a hold of that stuff was so impossible unless you're, head of state. So I, as a demonstration for my class, I ordered some on the internet and brought it in and showed it to them. And I said, well, I only got this much. I would have needed 20 times this to assassinate Litvinenko. So it would have cost me more than $10. So there's a lot of misinformation about radioactivity. Radioactivity is very common. But here's the problem. If you build a radiological bomb, as Jose Padilla, the Chicago street thug, who was supposed to release this in Chicago, you build something like this, the radioactivity is very intense. It's very hard to keep from killing yourself. And then you deliver it, and you blow it up. And once the radioactivity spreads out, there's something called the threshold effect. 1,000 rem will kill you within days. That's probably what Litvinenko got. If you have 100 rem, just 10% of that, you probably won't even notice it. You don't get sick. That's the threshold for radiation illness. So if you spread this out too much, like this much, there would be no dead bodies at the scene. Now, true, there's still a chance of it inducing cancer. And that's what happened at Chernobyl. So in Chernobyl, the radioactive plume spread, and we can calculate 24,000 people will die of cancer from the radioactivity spread like this. That's a really horrendous accident. The radiological bomb, you would probably get thousands dying, but you wouldn't see any dead bodies, and you wouldn't notice them because of the millions of people who die anyway. 20% of us, 1 out of 5, will die of cancer. If you want to increase that rate, you have to do a lot more than just a dirty bomb. So if Jose Padilla had done this, there wouldn't have been any dead bodies at the scene. Instead, they would be bragging that they had increased the cancer rate slightly in Americans. No, I mean, I'm not a terrorism expert, but I talked to a lot of terrorism experts, and their feeling was, no, that's not going to sell in the terrorist world, that yes, you've induced more cancers and they'll die. In Chernobyl, interestingly, although there was this movie, Chernobyl Heart, where they attributed every death in the region to the radioactivity, the fact is the people who died at the accident in the nuclear reactor from radiation illness, there are about 70 or 80 of them. There were about under 10 people who died of thyroid cancer, which is clearly due to this because of the fact that that's a relatively rare kind of cancer in any one city in Chernobyl. Beyond that, we expect 24,000, a huge number. But in that population, where there will be 24,000 people dying, there will be 3 million other cancer deaths from ordinary cancer. We don't know the cause of that. To see an increase of 24,000 in a population of, not a population, we're saying 3 million people will die of cancer from natural causes, it will not be observable statistically. It doesn't mean, this is a paradox here. You're killing 24,000 people who would not have died of cancer otherwise. But you won't see it. Does that mean it didn't happen? I mean, it sounds almost like the tree falling in the forest when nobody's around. This is a paradox I leave to my students because I can't resolve it, but it's something you need to know about. It affects nuclear waste storage too. And let me go quickly through this because I'm using up my time. I was talking to several people about nuclear waste storage. Nuclear waste storage drops off very rapidly. After about 100 years, it's down to 100 times worse than the uranium that was taken out of the ground. Now, if you could store that safely if you could store that with 10% chance that 10% would leak, you're even. Don't have time to go into the details. Be happy to answer more of some questions. My feeling about nuclear waste is it's fundamentally a solved problem except for the public fear of radioactivity. And the best thing we could have a new president doing is getting on television and talking in a nonpartisan way. Let's discuss the physics of radioactivity. You need to know about alcohol. You need to know about your own radioactivity, the radioactivity of the environment, so that you'll recognize that the restrictions being put on radioactive waste are so far down below the natural levels that perhaps we're overdoing it a little bit on the restrictions that we make. My own feeling, let me depart now from physics. I will give you my opinion. I try to not do this, but my own opinion is, and we have at least one real expert in the audience, Bob Budnitz, is that the nuclear waste storage problem is really solved, but it's not solved politically because there is such fear and hysteria about radioactivity that politicians hesitate to tread on this subject. Anyway, we're all talking to politicians trying to get that done, and we're not going to run out of uranium. Oh, so that's the bad news. The good news is, it actually after 100 years is not so bad. We have lots of uranium, so people think we're going to run out of uranium, and no, we're not. Okay, anthrax. Let me not go into this. Let me just tell you that at this point, I disagree with most of the experts. And I believe that the anthrax, what I did was, right after the anthrax was discovered, I went on the web to find out everything I could find out about anthrax. And it turned out there had been a Canadian experiment that had been published 3 weeks earlier. And this Canadian experiment had taken basically a half a gram of anthrax simulant, and they had put it in an envelope and opened it up in an office. And it had spread around the building, and they estimated that most of the people in the building would have died. This was what the experiment had done 3 weeks before this actually happened. My point is that the people who did this expected to kill hundreds, maybe thousands. They were not trying to do a demonstration. I've talked to directors of the FBI and all sorts of things about this. But anyway, my argument is there in the book. It's on the website. Okay, let's move on to energy. A couple things I want to point out here. A cluttered table. No, I don't expect you to memorize it. But there are lots of interesting things. We spent several lectures on this. Let me point out the energy of TNT right there. I think I have a laser here, but my laser is way too bright. I'm going to burn a hole in the screen. Let's see. Yeah, okay. So there's the laser. And everything is normalized to that. Call that unit energy for a pound or a gram of TNT. Chocolate chip cookies, 8 times more energy than TNT. That surprises a lot of people, but we use TNT because it releases energy very rapidly, and therefore you can get that hammer effect. So you can smash concrete. If you want to just destroy ordinary things like an automobile, don't blow it up with TNT. If you have an equal weight, Buy it in chocolate chip cookies, feed it to teenagers, give them sledgehammers, and you can do a lot more damage that way. And up here we get to, oh, this is interesting, gasoline. Look at that, 15 times the energy of TNT, more than chocolate chip cookies. This is really important in, and batteries. Yeah, the rechargeable, expensive computer batteries. They are 1/7 that of TNT. They're 100 times worse than gasoline. Expensive computer batteries, and they only last 3 years, as you know. They have what's called a calendar life, the lithium-ion batteries. This is why it's so hard to go. Who killed the electric automobile? Well, batteries aren't good enough. There's a lot of research, some of it being done at the Lawrence Berkeley Laboratory on improving batteries. There's a lot of hope, okay, look, the computer battery in here costs, it weighs a pound. It cost me $120. The Tesla Roadster uses these kind of batteries. They brag they use ordinary computer batteries. They have 1,000 pounds of computer batteries in the Tesla Roadster. If you bought that retail like I do, it's $120,000 just for the batteries. Of course, they can get it at a discount because they're buying so many, but they're only going to last 3 years. A good friend of mine has ordered a Tesla Roadster. He's promised to give me a ride on it. I'm looking forward to that. But you know, you got to be super wealthy to throw away $100,000, unless your goal, as I think his is, to pick up girls. So energy per gram, really important. Those are the gasoline. The huge energy per gram is what makes us, people say we have a love affair with gasoline. I think of it more as a marriage, an unhappy marriage, a marriage of convenience. And now we're running out and we seek a divorce, but it's going to be very expensive and difficult because gasoline a few years ago, think about what it was. It had this huge energy, 100 times as much as a battery. And not only that, but once you've burned it, it just disappears. No pollution. Throw some carbon dioxide in the atmosphere. Who worries about that? Okay? But no ash behind like coal. So it was the ideal fuel. And it's going to be hard to find a replacement. Let's look at the cost of energy. It's out of balance because our automobiles burn gasoline. T. Boone Pickens says, let's start burning methane. Why is that? Well, if you look at natural gas, it's a lot cheaper than gasoline. Well, here, that's a better comparison. It's 4 times cheaper. So switch to natural gas, burn that, you know, until the price of natural gas goes up. Coal is even cheaper. There is, okay, let's take a look at the countries. So this is out of whack because we happen to have automobiles that don't burn coal and they don't burn natural gas. And T. Boone Pickens wants to change that. I think that's a hard way to go. Oh, this is the last one here is fun. A AAA battery. This is for convert to electricity. So if you want to have a kilowatt hour of electricity, it will cost you 2.4 cents. You know how much it costs if you're going to get a kilowatt hour of electricity out of AAA batteries you buy at 7-Eleven? It's $1,000. There's one battery gives you a watt hour. And so for a kilowatt hour, that's $1,000. So, but we buy them anyway because when you know, hey, I have them in here. And this is a lot easier than hooking up to the grid, and I don't care if I have to spend $2 to do this. It's worth it. So there are these imbalances, and those imbalances have to be addressed so that we can use there are 2 issues that come up. One of them is called energy independence, and the other is called global warming. And let me give you my little, this isn't really physics, so I'm stepping off from physics again. You go up to any Republican and you say, global warming. And he'll say, oh, yes, global warming. And within 30 seconds, he's talking about energy independence, namely getting rid of our fossil fuels in the United States. Go to a Democrat and say energy independence, and within 30 seconds, they're talking about global warming. And you need to know these 2. And we'll get back to that and talk about some of the issues there. Fossil fuel reserves. This is a little bit of a cluttered plot. I hope you can see it. Over there, you may have a little bit of trouble, but I'll tell you what's there. These are countries. Their names are A, B, C, D, E. Those aren't their real names. I'll show you the real names in a moment. This has the fossil fuel reserves in oil, in coal, in gas, all put together, and then if you add in oil shale. If you put them all together, country A comes in top. First question is, where is Saudi Arabia on this list? Don't say out loud. This is a rhetorical question. I have to say that to my class. So where is Saudi Arabia on this list? In terms of total fossil fuel reserves, this is kind of interesting. Whoops. It's there, way down there. They got lots of oil. In fact, they're tops in oil. But they have no coal and only a little bit of natural gas. So they're way down there in fossil fuel reserves. What about China and India and Russia? Where are they? They're up there. Russia's number 2. China's number 3. Again, not a whole lot of oil. They have more than we have, but not a whole lot. But lots of coal, gas in the case of Russia. And so they're up there fairly high. What about the US? We're number 1. Not much oil. We're running out of oil, right? But huge amounts of coal, fairly large amount of gas. Actually, there's a lot more gas than that. And that's something that I've been studying and working on. But we have more fossil fuels than anybody else. Interesting down here is also Canada, which in terms of oil, you'll notice is second only to Saudi Arabia. Now, 10 years ago, they would not have been on this list. Did they discover more oil? No. No, 10 years ago, they had a lot of things called oil sands, and it cost you $50 or $60 a barrel to take it out, and oil only could sell for $15 a barrel, so it was unrecoverable oil. Now, once oil has gone up to $80, $90, $100 a barrel, that becomes economically viable, and suddenly they have the second largest reserves in the world. It's expensive, but they can do that. So when thinking about Hubbert's peak and the supply of oil and so on, you have to take into consideration the price. And that's happened with natural gas too. A lot of natural gas reserves in the US are now, people want to exploit them because the price has gone up to the point where it makes financial sense to do that. If you just make a plot of the total, including oil shale, here's the US. Next comes Russia. These are in total fossil fuels, and then China. And then Australia and India, and there's Saudi Arabia. Lots of oil, that's the orange. But we have huge reserves. This is great news for energy independence. This is terrible news for global warming. Okay, and yes, you can turn coal into oil. The Fischer-Tropsch process, you need to know about that. The fact is that it's just you got to build the factory, and then you could do it at about $50 or $60 a barrel. So if oil stays up at 100, the reason they're not doing this is largely the fear that the price of oil will come down as it has. Anybody check it today? What is it? No, I didn't mean gasoline. The price of oil, you think 90? Okay. See, it's getting dangerously close to the 60 at which the factory doesn't make sense. Okay, satellite spying. Don't really have much time to talk about that today. I want to get on to global warming. Let me just say that with this short observation time, the satellite goes over the Earth every 90 minutes. It goes over the thing you want to look at, maybe a centrifuge plant in Iran. And then by the time it comes back 90 minutes later, the Earth has rotated and it's not there anymore. It doesn't catch on the other side either. You got to wait 24 hours before you get another view. Of course, what happens is it's only if you watch satellites go over, these low Earth satellites that have the resolution, they're gone in about a minute. You've seen them. If you've ever gone camping, you see these satellites go over. And so all they have to do is cover up for a minute if they knew when the satellite was coming, which they do because amateur astronomers have made a hobby of this. And so on the web, they publish the orbits for the satellites. They write programs, so you put in your coordinates, when all the spy satellites will be above you. So this is, as from someone who worked at the other end of this, that's really annoying. You get a satellite up, and you can actually use it to look at some sites until the amateur astronomers figure out what it is and publish it. Future surveillance, I believe, is going to be done with drones. This is a photograph of a building you recognize, the Pentagon. Was not taken with light, was taken with radar. You can take images with radar, go right through clouds. These unmanned things carry that. This is the Global Hawk. It can take off from Ramstein in Germany. It can fly over Iran. It's as high as a U-2. Remember that? And I don't mean the band for the younger people in the audience. I mean the old airplane. It could go around for a day and then fly back to Germany, and could do this without a single human touching a button because it can find its own way using global positioning system satellites. This is the Predator. Oops, so let me just go through those. This is the Predator. It's the first drone to violate Isaac Asimov's rule of robots. This actually killed an Al-Qaeda operative in 2006. They shot a missile, spotted him. This is actually it's a solar-powered airplane done by Paul McCready. And this thing can stay up indefinitely during the day it charges its batteries and can fly at night. And I think these things are going to replace satellites for most of our spying in the next decade. Okay, let's get to global warming. A lot to say about global warming. There are anecdotes. So again, rhetorical question, but think of something that you know of from your own experience that illustrates global warming. And most people can come up with something like that. Forgive me for the following slide. This is not serious. Here's something else. We're somewhere near here. This is looking east on Durant, 1885. This is Berkeley. That's where the university is growing and so on. And there are some farms. Farms in Berkeley? And you'll notice the snow on the hills. Yeah, things have warmed up a bit. Okay, you never see that anymore. Here's global warming. This is the evidence. It's an organization you need to know called the IPCC. The IPCC stands for the Intergovernmental Panel on Climate Change. You don't have to know that. You have to know the IPCC is the scientific consensus that everybody refers to. Typical talk on global warming refers to the consensus. There is a consensus. Then they start telling you their own opinions. And you don't realize they're not talking about the consensus. This is global warming. This is the main evidence for global warming. The IPCC takes 3 bits of evidence. One of them is the rise of sea level. One of them is the melting of the Arctic ice. And the third and most powerful are the temperature records taken from thermometers. So this is global warming. Interestingly, in the latest report of the IPCC, 2007, the warming from the 1850s until 1957 is no longer attributed to humans in the IPCC report. That's because it really could be variations in the activity of the sun. And it's not much of a rise, and the activity of the sun was going up, so that could be that. We don't know, but it could be. The calculations that we have that go back to 1896 indicate that this probably is simply not human caused. Although many people will tell you about the warming starting in the 1800s, how this started coming in, the consensus of the IPCC is, no, you can't really attribute that to the humans. From 1957 on, however, the solar activity went down, and the warming kept on going up. So the IPCC concludes that this is the global warming. This is what's happening here. And my own opinion, I concur. So let's focus in on this most recent stuff, because I asked you about your experience. Just think in the last 10 years. Think of things that happened in the last 10 years. Don't say out loud that might be attributed to global warming. Okay, now, you'll notice the trend is going up, but there are all these fits and spurts, right? It goes up and down and up and down. So what happened in the last 10 years? I download this every month. I checked just earlier today to see if the latest month was there. It wasn't. So this is global warming for the past 10 years. This is in degrees Fahrenheit. By the way, if we go back to this one, you'll notice that the temperature rise is about 2 degrees Fahrenheit, out of which 1 degree Fahrenheit is attributed to humans. It's less than most people think. 1 degree Fahrenheit. How much of that is due to the US? We have done far more than our fair share in terms of population. We've probably contributed 1/4 of that. So the US is responsible for 1/4 of a degree Fahrenheit. And if we continue in the same way, we will be responsible for another 1/4 of a degree Fahrenheit over the next 30 or 40 years. Is that what we worry about? No, what we worry about is going up 5, 7, 10 degrees Fahrenheit. That's the global warming that we think is coming. It's not going to be coming from the US. Even if we don't sign Kyoto, it's not going to be coming from the US. It will be more than our fair share. We have no right, well, by population, to contribute another 1/4 of a degree. But you need to know where this, by the way, so the global warming of the last 10 years, there hasn't been any. But it's just a fluctuation. I believe It's a fluctuation, like these fluctuations, up and down and up and down and up and down. The temperature in this period has not gone up. That doesn't mean global warming isn't real. Global warming is real. 5 years ago, I wrote an article about this. I said, look, I've talked to the experts. Most of them agree we could have 10 years of no warming. And unless you let the public know that this is a possibility and it doesn't deny global warming, you're going to start losing people from your argument. The trouble is the US public doesn't pay attention unless you exaggerate. And so people have done that, particularly politicians. This is the IPCC. This is the consensus. This is the scientific consensus, the IPCC report. This is a quote. Basically, it says the climate change of the past 50 years is very likely not due to known natural causes alone. By 90%, that means there's a 10% chance it is due to natural causes. This isn't my opinion. This is the consensus. It's usually not quoted because most people want to scare their audience and they fear they will not respond unless they say it's imminent and huge and 100% likely. Well, anyway, that's not the scientific consensus. Al Gore is one who does this, and he got a Nobel Prize for alerting the US public and frightening the US public to do something about this urgent problem. But he did it, quite frankly, by exaggerating. There's the difference between his statement and what the scientists say. So I think you can handle the truth. The truth is, so far global warming has been very small, but that doesn't mean that it's not real. Why do they say 90% chance rather than 100% chance? Why doesn't the scientists say incontrovertible? And the reason is there's a big unknown called cloud cover. If cloud cover grows, then it could actually undo global warming. So as it gets hotter, you get more evaporation from the oceans. Evaporation from the oceans could create more clouds. We don't think they do. But it's hard to rule out. And that's why they give only a 90% confidence level, because 2% change in the cloud cover. Here are the detailed science things, which I won't go through right now. But the uncertainty in global warming, could it be that the human-caused global warming is in this range, or could it actually be all the way down to zero? The uncertainty all depends on the cloud cover. Anyway, let me not spend any more time on this, a lot of things. This is the expected global warming. This is why we worry. I blocked this thing out because this is the famous hockey stick controversy, in which I played a major role. And just these data are now basically flawed and known to be based on a computer bug, so forget that. But this was in the IPCC 2001 report. I can go into excruciating detail on that because I was involved in that. But the temperature rise, this is what we expect. And this is the range. Of course, there is some chance it'll be zero, and I'm praying for that. The reason I'm praying that it's not human caused is because I don't see any of our political leaders taking the action necessary to really do anything about this. That's not a physics comment. Okay, so let's move on. Some people say that global warming is based on all sorts of complicated computer calculations. Not true. It goes back to 1896 when Arrhenius did the first calculations. He showed doubling of CO2. He was the first scientist to really look at this. Doubling of CO2 would raise the temperature by 3 degrees Celsius. And then Roger Revelle College down in San Diego, a fellow that I'm honored to have known, in 1958, raised the issue again. He's the modern father of global warming. And he inspired a calculation done by some colleagues of mine, which is, I still think, the best scientific look at the subject. And they concluded that Arrhenius was right. Doubling of CO2, and we're going to get there. We're going to get there in 30 or 40 years. We're going to double the CO2. We'll raise the temperature by 3 degrees Celsius. The IPCC report, they used huge computer calculations, independent teams all doing the same thing. What they basically did is verify that Arrhenius was right. So we are not dependent on sophisticated, complex computer calculations. Back of the envelope calculation says, we really got to worry. We're now increasing the carbon dioxide. Let me skip to this. Well, here, let me go back here. Went one too far. Okay, there's a lot of thing in the news about the hurricane, increase in hurricanes. A complicated chart. You probably all know that hurricanes are increasing due to global warming. Hurricanes are also increasing because we have better observation of hurricanes. Katrina was a Category 3 hurricane when it hit the coast. It was Category 5 when it was out at sea. We call it category 5 because that's the maximum it ever got to. We're much better at observing these things. So there's a bias. We're observing more hurricanes because now we have the whole Atlantic Ocean covered with buoys and with satellites. So we see these hurricanes. So how much of the hurricane increase is due to better observation? There's one way that scientists typically handle this problem. And what they do is they take what's called an unbiased sample. Let's just consider the hurricanes that hit the United States. We observe those all the time. And when we observe them, they're not missed. So you could look up in the almanac at the hurricanes hitting the United States, and here's the record. The black lines are all the hurricanes by decade, and you can see the hurricanes hitting the United States have been going down a little bit. The really intense storms, the category 4 and 5 storms, that's this light gray thing. And statistically, they've been going down too. Hurricanes increase. The IPCC does not use that as a bit of evidence for global warming, because if you look at it scientifically, there's no evidence that in an unbiased sample, hurricanes are increasing. Doesn't mean global warming isn't real. But if you start cherry picking and picking every bit of evidence that sounds bad and attributed to global warming, you make a much stronger case, and you're much more likely to get the public. Here's a view of hurricanes of 1933. There were none out here. Now there are lots. It's purely observational bias. The cost of hurricanes has been going up. But not if you take into account the fact that we're putting much more expensive houses on the coast. Take that into account, you find the cost of hurricanes has not been going up when compensated for inflation and for the, this is one of the things that I object to in what Al Gore does. He shows a plot like this. It's not this plot, but he shows the cost of hurricanes going up, and he did not compensate for inflation. So it makes a very effective slide, but Greenland is melting. This is the observed rise in sea level. This is one of the key data points for global warming. It's going up, 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 up. Relatively steady. It doesn't go through those fits and spurts. So this is something to truly worry about. It's one of the 3 elements of data that the IPCC depends on. We can, based on this, which matches the observed global warming, we can predict how much the sea level will go up. And here are the predictions. This is from the Hadley Center, which is one of the major centers done in the IPCC. And here's the expected sea level rise. And you can see it goes up by 6 meters by the year 3000. By the year 2100, it goes up a couple feet. You need to know that the consensus is that sea level rise will not be a serious problem to Florida, to New York City, to places like that in the next 100 years. There are some islands in the Pacific that will be affected. But this is the consensus. If you see a film that shows New York City being flooded, it's all based on the hypothesis, which is not part of the consensus, that Greenland will become unstable and all the ice will flow into the sea, or Antarctica. The consensus is that that's not going to happen. Antarctica, well, so there, Antarctic ice is melting. It turns out that in 2001, the IPCC had their computer people predict how much the Antarctic ice would melt due to global warming. And what they concluded was it wouldn't melt, that because of evaporation from the oceans, you would actually have an ice buildup in Antarctica. And every one of the computer models predicted the same thing, an ice buildup in Antarctica. Then a couple years ago, what year was this? 2006. A couple years ago, an article came out showing that the opposite was happening, that ice was decreasing in Antarctica by 36 cubic miles per year. It's a lot of ice going away. It was widely reported as confirming global warming. The IPCC doesn't use it because it's exactly opposite to what you'd expect from global warming. So these anecdotes, I caution you not to, I mean, the fires on, last night, the fire on Angel Island, ready to attribute everything to global warming, but the IPCC has to be careful. Alaska is an interesting case. There's Alaska. This is the data. This is at Fairbanks. This is a smooth data. Typically, they'll plot a line like this showing global warming that's going up in Alaska. If you look at data in the North Atlantic, you find the temperature has undergone a big jump. They call this a regime change. Okay? And they don't understand it, but you can come up with models that will explain it. The interesting thing is it's very similar to what happened in Alaska. And so Alaska has been warm, for the last 25 years, but it hasn't gotten warmer. In fact, I was at a meeting just last week in which one of the Alaska scientists showed me data showing that the temperature in Alaska now is equal to the temperature average of the last 20 years. So Alaska is warm, but it's not warming. One Wildfires. This is one where I wrote to Al Gore. I tried to call him. I tried to contact him. He says that they're going up. If you look up the data published by the US government every year, they have an official report. It's going down. This is he hasn't gotten back to me on that. Then there's the tornadoes. Now, it could be possible that what he's doing is picking, he says they're going up, and the data says they're going down. These are only the strong to violent ones, the ones that actually land and do damage. It could be that the reason he says they're going up could be due to a bias from the fact that we're observing tornadoes much better now with radar than we used to. But the tornadoes, why would storms go down with global warming? Everybody says you have more heat, that's more energy. Well, storms come about from temperature differences. And it's equally plausible, because we know the poles warm up more than the equator, that you're reducing the temperature differences. And so you could imagine the storms going down. We don't know which will happen, but the evidence so far is that the storms have been going down. I fear that you will lose interest in global warming. And global warming is real. And there are those fluctuations. Now, in the last remaining 2 minutes, what can we do about it? Well, here's the problem. Carbon dioxide, very likely the cause of global warming, has been going up, up, up. Here's the US, more than our share. 1/4 of the car is going up, 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 up. Here we are. And we're beginning to slow down a little bit. You can see we're not rising as quickly as we used to be. But here are the developing countries, mostly China. And they have really taken off. Suppose we cut down to the Kyoto levels, 1990 levels. That's right here. Suppose we cut down to that and even go below that. And we go right here. We'll cut out this much global warming. And China and India will make up for that in 3 years. So we can feel good. I own a Prius. In my class, that gets me applause. Our house is all compact fluorescent bulbs. These are really nice feel-good measures. But if we make America completely green, all we're going to do is set an example for China and hope that they will follow and not first follow our other example, which is our standard of living. Okay, more evidence that they are really taking off. This is, it's called the non-OECD countries. These are the OECD countries, and they're really dominating. Part of the problem is that coal is dirt cheap, and they have lots of coal. And China's building, last year, 70 power plants, 70, each one the size of our biggest nuclear power generators, a gigawatt in each plant. And they're making these out of coal, and they're dirty. To take off my physics hat for a second, put on my political hat, personally, I see the only solution is we have to pay for them to use clean technology. They have no responsibility to do that. They're poor. The wealthy countries have to do it. This is what I would love to see our politicians suggesting, but I suspect that either politician who said we have to send $100 billion to China for clean technology would guarantee his loss in the election. Okay, conservation is the easy thing. This is a photograph I took of Notre Dame, and I took it of the chandelier here just to bring back and give a copy to my friend Art Rosenfeld, who was, along with Sam Berman and some others, the creator of the compact fluorescent light bulb. It came out of the Lawrence Berkeley Laboratory, the compact fluorescent light bulb. And now the chandeliers in Notre Dame. If you don't believe compact fluorescence can be beautiful, well, think of Notre Dame. Okay, so conservation is the real winner. There's so much you could be said about this. It's the easy thing to do. We have to do it ourselves. You make money by conserving. We have to pay for China, too. Maybe we can make some money on that. These are the various things that you could do. And efficiency is one of these rainbows or one of these wedges. Using renewables as some, nuclear as some. I hate it when my friends start arguing that we shouldn't have nuclear because we should do it with renewables. Realistically, we need everything. Let's not argue among ourselves as to which one of our green solutions is more righteous. That just does harm. McKinsey showed that it's really cheap. You save money by doing conservation. This is the inefficiency. This is how much energy you use for a given unit of GNP. And the countries that are doing the worst, of course, are the developing countries. Developing countries always do badly. China and India, the US is down there. And if we use conservation measures and get China to use them too, we could be using less energy by the year 2100 than we are now, less energy per year, and yet have every single Chinese and Indian person living at the European standard of living. So there's great reason for optimism. Anyway, let me just finish up. Clean coal is not an oxymoron. Yes, you can do it. It means taking the carbon dioxide and putting it underground. I believe this is a feasible technology. I think it's one of the more straightforward technologies. People say it's unproven, but I think it is less unproven than many of the other things that people would like to do. There's some more details on it. Solar cells are coming along really quickly. I think we're entering a really exciting period of solar cells. Wind turbines, see those two pictures there? Those are to the same scale. That's an 8 megawatt wind turbine in Germany. And T. Boone Pickens is right about that. We have a good wind corridor in the US. We just have to find ways to bring that energy back to the cities where they need it. So let me finish up. The public needs to know this stuff. Most of this is completely nonpartisan. It doesn't have to be taught with spin. But I think what we need to do is to agree on the physics. I'd love to see the president every month say, today we're going to have some physics discussion, or maybe some chemistry or biology. And I'm going to give you the true non-spin stuff. I'm not going to put, this is going to be nonpartisan. Let's just for an hour talk about the things you really need to know. We'll agree on the physics, and then you can decide on nuclear waste. And at that point, once we've agreed on the facts and the levels of radioactivity and what they are, then you may decide you don't trust these people to handle the nuclear waste. And that's fine. But that's the politics and the trust aspect of it. The physics we should agree on. We should know we're all radioactive, what the levels are, and what levels cause cancer, and how this compares, and all that kind of stuff. So likewise on terrorism, likewise on energy. We need to know, the public needs to know that batteries, if they can be improved, are very important, because then we can have automobiles without gasoline. But that batteries have to be improved by a big factor before China and India can afford them. So here are some of the things I didn't touch on. And yeah, there are lots. Some of these things go into my book. But in the end, if you want more, go to my webpage, www.muller.lbl for Lawrence Berkeley Laboratory.gov, and you'll find links to my class and everything else. So at this point, all I can say is good luck in your campaign. Thank you. So I'm ready for some lively questions. Yes?
I remember reading an article in the newspaper with some photos, and it was interesting. It was about Greenland, and it was talking about some of the dogs there who no longer have their job much of the year because the snow has melted and the ice as well too. And I was wondering how that fits into this.
Okay, the question is, there were some news stories about the melting of Greenland, and how does that fit in? From the experts I've spoken to, the melting of Greenland is largely an effect of soot coming from coal-burning plants in the United States, which lands on the ice and tends to melt it. We obviously have to do something about that. There's also an acid rain issue. The experts, that warming from this is probably responsible for the disappearance of ice in the Arctic Ocean, but probably not responsible for the melting of Greenland. That's another cause. The reason it's important to know that is that if you think it's global warming, there's nothing you can do about it. Right? Hey, we got to get China and India to cut down on their CO2. That's going to cost us hundreds of billions of dollars. But if you recognize that this melting here is probably due to a local effect due to power plants in the US that are spewing soot on Greenland, then we can actually take action. So this is why it's dangerous to attribute everything to global warming. Yeah?
You focused exclusively on physical science and physics.
Right.
What about Ecology 101? What would they be telling the president given the decimation of species and Sylvia Earle talking about destruction of oceanic species?
Oh yeah, so the question is, what about Ecology 101, destruction of species and so on? That's another subject in which there's a huge amount of really important things for the president to know, some of which I touch on in physics. I happen to know more about physics than I do about some of these other subjects. The issues of species disappearance is also very interesting because there are observational biases, and most of the disappearance of species, it turns out, take place in the Amazon, where they make an assumption, a very critical assumption, that there's a huge diversity across the Amazon that has not been verified, but which is plausible. Most of the species that are disappearing, most people have trouble trying to think of one mammal that has disappeared. Some people know more than others. The effect is one that is a fascinating one on which I'm not an expert. I'd also like to see biology and medicine. I think the president needs to know about stem cells, needs to know what happens to them if you don't destroy them in one way. Lots of issues. I think physics is just one of them. Absolutely right. More questions? I've tempted to shine the laser at you, but I won't. Yes?
I saw in your graph all that oil shale that we have.
Oh, yes.
What's the price threshold that's going to make that economically and environmentally viable?
Okay, the question is oil shale. U.S. has huge amounts of it. What's the price threshold? My guess is it will not be exploited until we exploit the coal, because that's cheaper. And the natural gas, of which we have huge amounts. I don't exactly know what the price threshold is for oil shales, but for coal to liquid, it's about $50 or $60 a barrel. And for natural gas, there's a lot that can be drilled that hasn't been drilled, largely because of local effects. People are worried that what you have to do is you have to pump water down into these mines to crack the rock so the gas can come back up. When you do that, some of the water comes up too, and you dump that down the local river, and that's been a major cause of objection. That, of course, can be cleaned. It just takes a little bit more money. But it has a bad reputation because they didn't do that in the past. So my guess is that that natural gas and coal are the cheaper things to do than the oil shales. Okay, in the back, yes.
You mentioned in carbon sequestration went by very fast. They said you can't suck CO2 out of the air.
That's right.
That is, in fact, the problem. How do you concentrate the CO2?
Okay, so the question is, I said you can't suck carbon dioxide out of the air. You only capture it when you're burning the fuel and then put it underground where according to the carbon sequestration ideas, there's a big IPCC report on that too. What you do is it dissolves in the deep sea brines. So I say you can't suck it out of the air. There's a $10 million prize for someone who figures out how to suck it out of the air. From the physics point of view, I've just decided that looks like a totally untractable problem. That could be considered a challenge for some of you. But once it's in the air, it stays up there. And as we dump more and more into the atmosphere, it stays up there for hundreds of years. Eventually, it will dissolve in the oceans, but only as the oceans overturn, so that fresh water comes up, which have not yet reached equilibrium with the atmospheric carbon dioxide. So carbon dioxide is a really long-term problem. Methane, in contrast, has a half-life of 7 years. So it actually converts into carbon dioxide, but it's much less of a greenhouse gas in that new form. So there's a serious problem, and I don't see a solution to removing carbon dioxide from the atmosphere. You could try building more trees and so on, but that only scratches the surface. I think that's very, we're stuck, and we keep on going up. Yes?
Yes, there's a process I read about cement being, manufactured cement puts a lot of carbon dioxide out, and there's a new process that uses carbon dioxide power plants and bubbles through seawater to create cement, and would sequester that.
Right. Okay, the question has to do with cement, that we thought China would surpass the U.S. in carbon dioxide in a few years, but when we included in the cement processes that they're using, it turns out they already surpassed us. So cement is a major producer of CO2, but there are new processes that talk about taking that carbon dioxide and then using that to create the calcium carbonates. You get the calcium from the seawater. You can create cement that way. So people are talking about sequestering carbon dioxide in cement. It's a relatively new idea, one that I haven't looked at very seriously. The advantage, of course, is that you wind up making something you can sell. So it's an intriguing idea. It's probably more expensive than sequestering it underground, but I'm not sure. So there are these new ideas coming out. The question there, yes?
My understanding with this sequestering the concrete, as the concrete heats up, you want a reaction to go, you heat it up, and it's going to come out. other countries copy us, and we have a wasteful, we should be copied when we've cleaned up our act, and that's these filthy oceans, the plastic. And the last part of what I want to say is it appears to me from what I've been reading that people, like some of the scientists at Berkeley Lab, want the Arctic to melt because all the oil is under it, and they want to continue what they're doing. But I think we need to clean up before we go forward with any more things that are creating havoc with it.
Okay, I'm not sure I can do.
The trees have been cut, and the trees take the carbon dioxide out, and so we don't take the trees lightly.
I wish you had a microphone because I can't really do justice in trying to say all the points that you made, other than you don't like what I said because I'm talking about markets operating. And I hope you recognize that I step aside when I talk about my own political solution, and that's not the essence of what I'm talking about. Most of what I'm talking about is how difficult the problem is. And I step aside when I say I'm not optimistic that if I were the premier of China, or if you were the premier of China, you know, would you say, okay, I have all these impoverished people, I have all these people with no education, I have all these people that suffer periodic starvation, but rather than have my economy grow exponentially, I'm going to cut back because I don't want the world to rise 5 degrees. I'm not optimistic that the leader of China would do that. I'm worried that they will put as a higher, this is politics, not physics, I'm worried that they will put a, what's that? Oh yeah, we can do it and delay global warming by 3 years. That you need to know. You need to know that if we cut back, yes, we can set an example. And at this point, we're out of physics. What you need to know is that the physics is if we cut back and they continue, we delay global warming by 3 years. That's physics. After that, then it becomes the politics of whether we setting an example will do it or not. And that's the sort of thing that reasonable people will reach different conclusions on. You didn't like my conclusion. Okay, fair enough. Are you flooding me or her? Yes.
I'm just curious about, we're talking quite a bit about nuclear radioactivity. You said it would be very difficult for Jose Padilla, for example,
To make, as you go along, in case this is long, let me just say that you've said that would have been, you're pointing out that I said that it would be very difficult for Jose Padilla to have made a dirty bomb.
correct, okay. So, but I guess I was listening to all of that, and I happen to be related to someone who survived the bomb that was dropped in Hiroshima, and I rarely hear the connection made between sort of uranium and plutonium, what am I trying to say, discovery to actually another bomb being dropped in the world. Like, I kind of miss the fact that no one really discusses that this tragedy can happen once again. So beyond cancer, 24 million people or 24,000 people dying from cancer, I mean, that was utter devastation. And
That wasn't Hiroshima, that was Chernobyl.
right.
At Hiroshima, 2% of the victims died of cancer.
Right. The rest of them.
The rest all were blasted away.
Right, but then the survivors, right?
I mean, of the survivors, you take the total number of survivors who died from cancer, according to the UN estimates, and these are good estimates. They say, let's take the number of 50,000 people were killed in the blast. Some people say 75, some people say 100, hardly matters. About 2,000 deaths, 1,000 or 2,000 deaths from cancer induced by that bomb. That's the best estimate that people have.
Right, and I guess I shouldn't have even mentioned that, because my question is, has that gone away as far as a fear or a possibility that someone could just go ahead and drop?
Because the question is, has the fear of nuclear war gone away? Because I didn't mention it in my class, you know, in what I'm doing. And some people, I have good friends, Sid Drell, Dick Garwin, who would come up here and they would give their talk, and their primary emphasis would be on the danger of nuclear warfare, okay? And my own personal evaluation is not to include that because I see so many, to me that's something that I grew up with, I was scared of my whole life. And now the Soviet Union is gone. My personal opinion is that the Holocaust of nuclear warfare is not what I really worry about anymore.
But it hasn't become easier because of like newer research.
Well, the question is, has it become easier because of new research? No, it has not become easier. I mean, North Korea's bomb was a fizzle. It's still hard to make these things. There were bombs that were successfully made by India, by Pakistan. I talked to someone recently who said the Indians made their bomb not because of Pakistan, they were worried about China. Interesting insight. Delivery of the bombs, I mean, these missiles are things that only a few countries have. And I don't think, this is a political evaluation that some of my colleagues disagree with. I'm not personally worried about the big Holocaust anymore. I'm much more worried about the next terrorist attack or global warming. Yeah.
When I think of coal, I don't think of a clean energy source. So what are people talking about when they say clean coal?
Okay, clean coal has two definitions. There's the old definition, in which they mean you don't want the soot coming out, you don't want the sulfuric acid coming out, you don't want the mercury coming out. So they make stacks that clean this stuff electrostatically. It costs a little bit, but this is being adopted by most plants. The Chinese will do that because it's a health issue in their own country. The new clean coal, when Barack Obama says clean coal, he's referring to the next step beyond that, which is the carbon dioxide that's coming out, you grab it and you bury it underground where it dissolves in deep salt brines. And that's what he means. That's what McCain means when they talk about that. So now we're talking about burning coal, but not contributing to global warming. That's what is meant by the new clean coal. It's easily confused with the old clean coal. Follow up?
That science exists now?
You know, it's been done in a few places. People say the science exists. It's really a technology issue. It has to be tried. These deep salt brines have not been tried as far as I know. I regard that as much more straightforward than, let's say, developing cheaper batteries. You know, if you put or cheaper solar cells so that China can really afford to use them for a large source of their power. Of the various things that are being done, I regard sequestration, carbon capture and storage, CCS, as relatively straightforward compared to some of the other much more difficult. Over here, yeah.
You were talking about terrorism and dirty bombs, and I agree with you completely that dirty bombs from a physics viewpoint are very ineffective. But from a terrorism viewpoint, because terrorism is aimed at causing disruption to society, and because of the perception of a dirty bomb, because of the political reaction to a dirty bomb, a very small amount of radioactive material can have a tremendous...
Okay, let me, what he's saying is that dirty bombs would have a terrorist effect way beyond the actual deaths that they would cause because of the spread of radioactivity. And that's your point.
And it's political because they would cordon off huge parts of the city.
And they would cordon off large parts of the city and evacuate and so on.
So the
Yeah.
reaction to it would be tremendous even if the physical
Okay.
effect-
So what he's presenting is the point of view of those friends of mine who think I'm wrong on the dirty bomb issue. Namely that it will spread terror because people are so afraid of radioactivity. You may be right on that.
And it's an education issue.
But it's an education issue. And it could as easily be that once the dirty bomb spreads this radioactivity, people go around saying, so now if you live in this area 24/7, your chance of cancer will go up from 20% to 20.01%. Some people might choose to move back in. It may be an educational thing that once the dirty bomb goes off. From the terrorist experts I spoke to, they say that the terrorists want dead bodies. They want to count the number of dead, not the number of dying someday.
In the diagram you showed of the potential dirty bomb in Manhattan, there were several areas that there was permanently closed.
Yes, the Scientific American article had regions that were permanently closed. I don't believe that article. I was showing you, okay? More questions? Good point. Yes, was that, yeah. I can't see your questions.
You haven't touched the possibility of these positive feedback loops with regard to global warming. Therefore, you're basically implying that the inputs are linear, and I'm not sure that's...
Okay, the question is positive feedback loops in global warming. There are, many of these actually are included in the IPCC report. For example, the moisture coming up is a major greenhouse gas. And that's a positive feedback. There are some things that people talk about that are discussed, and the possibility that, for example, methane will be released from the permafrost in Siberia if we get up to a certain level. And I actually just spoke to some experts about that last week. The best calculations indicate no, we're nowhere near anything like that happening. But these are the sorts of things you worry about, and you have to find them. There's the positive feedback that if there was worry for a while that the ice shelf, the southern of Antarctica, the west ice shelf would go into the sea. And more measurements and so on, that turned out not to be a worry. So no, there are positive feedback things that people worry. They're just not part of the consensus. And I tried not to include the speculative things that drive science. Someone has an idea and they write an article about it and it gets a lot of attention, but that happens both ways. And I tried to, the consensus is that that if you're talking about the methane in the Arctic, the consensus is that that's not really a danger. Although there are some scientists who keep on pushing the point. Did you have some other positive feedbacks in mind?
I'm not the golden.
Okay. Okay, question, where have I not gone? Over here, yes.
You spoke about the 9/11 collapse of the World Trade Center as being unanticipated.
Right.
But I'm under the impression that they had captured some terrorist in the 90s with plans to fly airplanes into tall buildings, and that they prior attack on the World.
Okay, may I address that?
Excuse me?
May I address it? I'm trying to keep the questions short, so because I have to repeat them, and it's not easy. So you are saying that it was an unanticipated attack. What I really meant when I said that the collapse was unanticipated. The idea of flying an airplane into a building, I think, should have been anticipated. But the idea that the building would collapse from the top down, as far as I know, was not something that was in the mindset of anybody who was working on, or who was worried about those issues, including the firemen and the policemen. I didn't mean to say that the idea of hijacking an airplane, that appeared in some novels and so on. That's not what I meant, okay? So if you can keep the questions short, then I could state them over again. If you just talk and give your...
We have time for 4 more questions.
4 more questions, okay.
I want to find out what is the physics of water, potable water, which is the stuff of life, and the coming water wars, the politics of water.
Okay. The question is water. What is the future of that? What is the physics of that? Let me just say that I was talking last week to a top scientist who has actually made major inroads into global warming and has had an enormous effect, I think, and what he is thinking of doing is spending the next 10 years of his life on the problem you mentioned, the problem of potable water around the world. And it's an interesting problem. It has some physics aspects, some other aspects. I think you've identified an extremely important subject for which there is physics spin. At the Lawrence Berkeley Laboratory, Ashok Gagil invented a way of cleaning water that could be used in his home country of India in poor villages. It's a very simple system with a fluorescent light bulb. It's actually one of these fluorescent light bulbs that has the fluorescent thing removed, so it's ultraviolet. And he has built these things and set them up. In India, he's done similar things in Africa. He's one of the great heroes of the world, Ashok Gagil. Remember that name, so when he wins a Nobel Peace Prize, you'll say you heard it here. And his primary concern is pure water for people who are not getting it. There are some amazing things you can do with a little bit of physics. So it's a great, great subject. It's not in my book, I'm afraid. Okay, more questions. Yes?
So I took a physics class from you about 4
You
years
next.
ago.
He took a physics class from me 4 years ago.
12.
12? Okay.
And you talked about nuclear power, and it's pretty much the same talk that you gave tonight.
Okay.
In a lot of respects.
So he says he took a class from me 12 years ago, and I'm saying the same thing about nuclear power I said back then. Go ahead.
And the public perception of nuclear power radioactivity hasn't changed at all.
And he says the public perception of nuclear power and radioactivity hasn't changed. I think you're wrong on that.
Okay.
I've seen some attempts to measure the public sense of nuclear power, and the fear and dread of nuclear power has really been going down rather dramatically in the last 10 years, probably due to several things, the most of which is that young people don't remember 3 Mile Island. and so anyway, I think it really is changing. Go ahead.
Well, my broad question, though, is how can science be an active tool to actually change perception?
Okay, so how can science change perception? I think what we need is, I hate to say this, less scientific advocacy. I think scientists are beginning to be felt as if they're another special interest group, that they worry we spin our science because I wish to convince you of a certain conclusion. I did some of that here, but I tried to keep it down. I think there are things that we need to agree on, And once a scientist becomes an advocate, people don't trust his science anymore. And I feel there's been too much of that, and it's been eroding confidence of people in science. Question right behind you. There goes the mic. Who needs a mic? Yes.
Well, I happen to be a son of a bomb survivor from Hiroshima, and my mother died 3 years ago from cancer. But the question is there any solution for mounting nuclear waste?
Okay, the question is there a solution for the increasing levels of nuclear waste? Okay, I believe there is, and I think the physics is solved. The public relations isn't solved. There's so much fear of it that people are using the politics of this for their own purposes. I believe that Yucca Mountain, for example, is one of the least dangerous things. If we were to use it and store all of our nuclear waste there, we can't store all of it, but if we store nuclear waste there, it will be one of the least dangerous things that we have to worry about. Much less dangerous than terrorism, than global warming, than war. People talk about nuclear power, and they say, what about Chernobyl? And I'll ask, this is politics again. Okay, what's the Chernobyl of oil? If you think about it, two things come to mind. One of them is global warming, and the other one is war in the Mideast. So when we're comparing nukes to oil, of course people say, oh, no nuke, let's go solar. But solar right now is too expensive for China and India to use except in specialized applications. So they are going coal, whole hog. I would much prefer them to be going nuclear because I think the dangers of fossil fuels, in my mind, are much worse. Question here. Oh, reprocessing is, the question is, do I cover reprocessing? A bit. Preprocessing is the process of taking, you put uranium in a nuclear reactor, and after a year, there's quite a bit of plutonium in it. The plutonium is generated in a nuclear reactor. At that point, you take the spent fuel out, it's highly radioactive. Reprocessing is the process of taking out that plutonium to use elsewhere. You can use it in a bomb, or you could use it in another nuclear reactor. People have opposed this in the past because of what they call they don't want the plutonium economy. If plutonium becomes a commodity, then it will get diverted, and we could have rogue nations or terrorists or even our friendly nations using the plutonium in a bomb, and this could lead to nuclear war. So that's an argument against the plutonium economy. But reprocessing is that procedure of taking the plutonium out of the fuel of the nuclear reactor.
Are the French doing it?
The French are reprocessing, and we are not. It was a decision made years ago for various reasons, part of it being political. People were afraid of the plutonium economy. This way, we didn't have to address that issue. Part of it was financial. It's actually cheaper to get, right now, a substantial fraction, I think 1/4 of the uranium and plutonium that we're using in our nuclear reactors actually comes from old Soviet nuclear weapons, which were purchased from them. So that's fairly cheap and cheaper than reprocessing. So there's a financial aspect to that. Another question? Yes?
How safe are the compact fluorescent lights?
Oh, how safe are the compact fluorescent lights? Yeah, all fluorescent lights have a little bit of mercury in them. And so they give you these procedures that if you break one, if you actually look at the procedures, you realize that those procedures are designed to prevent them from being sued. They're not designed because you actually need to go through those procedures. So yes, mercury is a danger. I would be much smarter today if I didn't play with mercury with my fingers when I was a kid, which I did. Used to pour it back and forth. Ooh, mercury, wonderful stuff, yeah. So there is some danger from mercury, and I will tell you, since I'm speaking publicly, I don't want you to sue me. If you break a fluorescent bulb, and most of the people here over age 30 have broken a fluorescent bulb once or twice, there's a little bit of mercury inside, a very small amount, tiny compared to the amount I used to play with. It is a poison, it is dangerous, but I think the compact fluorescent bulbs are really tough, and I've filled my house with them.
I was wondering about the mercury that goes into the landfill.
The mercury that goes into the landfills from thrown out compact fluorescent bulbs, it should be recycled. You're welcome. More questions? Okay.
Okay. Well, thank you, sir. That was really wonderful. I need to take a class now. We have a gift.
Wow, just what I... This is why I gave this lecture.
Yes. Well, I hope you wear it proudly.
The element named after Lawrence Berkeley Laboratory physicist, chemist, Len Seaborg, who in fact discovered plutonium. An element named after him.
And I didn't plan that. So thank you so much for your talk, your questions. You can continue the questions, I assume, during the book signing if people have questions. There are plenty of books out there for signing, and I want to encourage you to come see Dr. Muller's student, Saul Perlmutter, is going to be here on November 24th, 5:30. It's the Monday of Thanksgiving week, talking about dark energies discovery, and hope you can join us then. And thank you very much. Thank you so much. Really, I learned a lot.